Greetings. I think we've seen enough of first order differential equations for now, so let's take a look at second order. That means, of course, that there's a second derivative in the equation, and of course there could be a first derivative and the function itself, just nothing higher than second derivative. We're going to be focusing on linear second order differential equations to keep things simple for now. Linear in this case just means we're dealing with linear combinations of these terms. So some function of t times y double prime plus some function of t times y prime plus some function of t times y itself equals presumably some other function of t. And to simplify things even further, to start with, we're going to assume that these coefficients are not any functions of t, but specifically are constants. So let's assume that these are constants times y and its derivatives, which means we can just write this as a times y double prime plus b times y plus c times y prime plus c times y equals, and then this could be some function. But the simplest function to work with here would be 0. In that case, if the ay double prime plus by prime plus cy equals 0, we call this a homogeneous linear first or second order differential equation. If it's not 0, this g of t thing is called the non-homogeneity, because it's what makes it non-homogeneous, or sometimes called the forcing function. Because in applications in physics, this extra term usually represents something outside the system that's exerting a force on the system. Or in circuits, something exerting an extra voltage, like a battery or a generator. And it doesn't have to be on this side of the equation. You could rearrange these terms however you want. The important thing is the non-homogeneity is the term that doesn't have y in it at all. So that's the main idea. Second order linear differential equation with constant coefficients, and for now we're going to assume it's homogeneous. We'll get into non-homogeneities later. Let's try out a simple example of this. This equation is simple enough that we may be able to solve it by inspection. Solving by inspection basically means you look at the problem, you think very hard for a moment, and you say, oh, obviously the answer is this. Of course, the problem with this is that what's obvious to one person might not be as obvious to another. But let's see if we can think this through. We're looking for a function whose second derivative equals the function itself. What function do you remember from calculus where taking the derivative twice doesn't change it? Do you remember e to the t? We already saw that its first derivative is just itself, but that means its second derivative is also just itself. So if you fill these back into the original differential equation, y is e to the t, y double prime is also e to the t, so y equals e to the t is one of the solutions. But it's not the only solution. Can you think of another function that also has this same behavior, where the second derivative loops back around to be the same function? It's another exponential function, specifically e to the negative t. Because if you take the first derivative, the chain rule brings out an extra negative. So y prime is not the same as y, but take the derivative again, bringing out another negative from the chain rule makes it positive e to the negative t, which is the same as the original function. So e to the negative t also makes this differential equation true. This second order differential equation has two different types of solutions, and that's generally going to be true for second order differential equations, at least the linear ones we're going to be looking at. Since we have two types of solutions, we usually call those y1 and y2. But as with first order equations, there's actually infinitely many solutions, not just these two. And how do we build more solutions? This is where the idea of linear combinations comes in again. If we add these functions and take the second derivative, e to the t becomes e to the t, e to the negative t becomes e to the negative t, and then positive e to the negative t. So once again we have this function's second derivative equals this function itself. So if you add together two functions that are both solutions, you get another function that's a solution. Also, if you multiply one of these by some scalar, let's say you take maybe 5 times y1, and take the second derivative. 5 is just a constant multiplier, so that's going to stay the same. We get 5e to the t as the first derivative, 5e to the t as the second derivative. So that means some scalar multiplier times e to the t is also a solution. And it turns out this is generally true as long as the original differential equation is linear and homogeneous. Because a solution of a differential equation like that, in this case for instance e to the t, you plug that in, it makes this whole thing add up to 0. If you plug in a summation or a multiplier, a scalar multiplier times a function that makes this true, these distribute across the addition. You can pull a scalar multiplier out of the derivative, and you end up with a linear combination of things that add up to 0 anyway. So in general, if you've got any two or more solutions of a linear differential equation that's homogeneous, linear combinations of those solutions will also be a solution. Linear combination in the sense that you can multiply each one by a scalar, which we usually call C1 and C2, and then you can add those together. So this would be the general solution. In this case, y1 and y2 are just e to the t and e to the negative t. So there's our general solution. This linear combination of the two types of solutions we found should cover all possible solutions of the original differential equation. And this is usually called the principle of superposition. The idea that we can combine solutions we found using the idea of linear combinations to get more solutions. And what if we wanted to narrow this down to a specific solution instead of infinitely many solutions? We need to find values of C1 and C2, so as before, we'd look to initial conditions. And let's say we have initial conditions here. Let's say we know that when t is 0, y is 5. If we write out our general solution and fill that in, we get y being 5, c1 times e to the 0 is just 1, c2 times e to the 0 also just 1, so 5 equals c1 plus c2. But that's not enough information on its own. We've got two unknown variables, so we need two equations to be able to solve. So we're going to need one more piece of information. That other piece of information is usually not the y value, but the y prime value, the derivative. That is, how fast y is changing. So for a second order differential equation, we're going to need to know essentially where the object is at time 0. If you think of y as position, we need to know where it is at some time, and also how fast it's moving at some time, the velocity essentially. It doesn't have to be at the same time, but it usually is. Let's say when t is 0, y prime is negative 3. What we can do with that is take the derivative of our general solution. In this case, that'll be e to the t is still just e to the t. E to the negative t becomes negative e to the t, negative t. So now we fill in our initial conditions for the derivative into the derivative of our solution. We get negative 3 equals c1 e to the 0, so that's just c1, minus c2 e to the 0, so that's minus c2. And now we have a system of equations we can solve for c1 and c2. For example, in this case, we can just add these together. C2's cancel out, so C1 is 1. Fill that in here. 1 plus C2 is 5, so C2 is 4. We can now fill those in for C1 and C2 in our general solution. C1 being 1, C2 being 4, and this would now be the specific solution that obeys these initial conditions. So in general, for second order differential equations, once you've found your general solution, you're going to need two pieces of information for the initial conditions if you want to solve for a specific solution. And those are typically going to be the position and velocity, that is the value and the first derivative at some instant in time. Usually time 0, but doesn't have to be. So let's try out a more complicated example. This example looks too complicated to solve by inspection like last time, so instead we're going to use a technique that you're going to be seeing quite a lot in differential equations. We're going to guess. More specifically, or more formally, we usually call this the Unsats method. Unsats being a German word for a starting point or a baseline or the way you lay out your tools when you're ready to begin working. The idea is we're going to make a guess, but it's going to be an educated guess about what we think the solution should look like. Sort of a general format of the type of function we think it's going to be, but leaving some unknown parameters so there's some room for flexibility. In this case, the only thing we really know is that the function and its derivative and its second derivative have to be able to combine together to get 0, to cancel out. So we should expect y to be some sort of function where taking the derivative doesn't change what type of function it is. And what's a function we already know that stays the same type of function when you take derivatives? Exponential should work fine. But it's not just going to be e to the t. Presumably it's going to be e to the something t. So let's say e to the rt, where r is some unknown parameter. This will allow some flexibility, and ideally we want to figure out what r is. Our next step, we're going to take this function and its derivatives and insert those back into the original differential equation. So of course when we take the derivatives, y prime, e to the rt stays e to the rt, but the chain rule brings out an extra times r. Y double prime, e to the rt still stays e to the rt, but we get another times r, making it r squared. So if we fill these back into the original differential equation, y double prime is r squared e to the rt plus 5 times y prime, so 5r e to the rt, plus 6 times the original function, our guess, e to the rt, and we want to make sure that adds up to 0. Now this equation essentially is going to tell us two things. First of all, it's going to tell us, is this guess even valid? Does it even work? And second, it allows us to figure out what values of r or any other parameters will make this work. In this case, we've got e to the rt in every term, so we could divide that out. Let's just go ahead and divide both sides by e to the rt. And we end up with r squared plus 5r plus 6 equals 0. In other words, a quadratic equals 0. And it's certainly possible for a quadratic to equal 0. So that suggests this should work as a solution as long as we can find the r value that makes this work. This, by the way, is usually called the characteristic quadratic of the differential equation. And the nice thing about this is that we know how to deal with quadratics. We've been working with quadratics since forever. So we have this quadratic. As long as we can solve this quadratic, we'll have a value or values for r that we can fill back in here, and we'll have a solution. And how do we solve a quadratic? Lots of ways. You could factor it if it's factorable. This one does look factorable. If it's not factorable, or if you don't see an easy way to factor it right away, you can use completing the square or the quadratic formula, or even graph it and see where it hits the axis. In this case, it looks like we can factor this. It looks like it factors to r plus 2 times r plus 3. So our solutions are going to be -2 or -3. We could call those r1 and r2. Fill those back into our original guess, and we get e to the r1t and separately e to the r2t. So that looks like e to the -2t, let's call that y1, and e to the -3t, we'll call that y2. So we have two different solutions. These are usually called, by the way, a fundamental set of solutions for the original differential equation. And as before, we can combine those to get all possible solutions, the general solution, by using the idea of linear combinations. C1 times y1 plus C2 times y2. So this would be the general solution, describing all possible solutions. It's got two unknowns, C1 and C2, because we got two r values, because it was a second order differential equation. That means we'll need two pieces of initial values to solve for it, presumably y at some time and also y prime at some time, probably times 0 to make it easy. So there's our solution, our general solution. Give that a try with some other examples yourself. And the thing is, this is really easy to make more examples. If you have any quadratic that you know how to solve, you can turn that into a differential equation that you now know how to solve. For example, if we take a look at the quadratic r squared plus 10r plus 16 equals 0. This is a quadratic you should be able to solve. We can turn that quadratic into a differential equation that you should now know how to solve. So try solving this differential equation. Again, you can guess y equals e to the rt, plug in that function and its derivatives, it should turn into the characteristic quadratic, and see where you can go from there. So try making up some more examples using any quadratics that you know how to solve. Again, it doesn't have to be factorable. Even if it's not whole number solutions, you can still use the quadratic formula or completing the square. And next time we will take a look into some of the theory of how and why this all works. See you then.